So, hello to all the friends that I have on YouTube. Probably not a lot, but anyway, today I was looking into the light specs that you need to grow your plants inside, and quite frankly, there's a lot of stuff on YouTube, and most of them say that how is it called? White light is the best light, and based on what I found, I came to a similar conclusion. So if that's all you needed to know, then you can just quit this video and just go on with your day. But if you actually like to get a little bit more into the details, with the details I mean actually the entire story as to why or why not, just vote. Why or why not is just more or less efficient to use red light, then just stick to it because I want to go over everything that I looked into, and everything that I looked into is quite a lot. So I'm not gonna say what I'm gonna cover. You will just have to stick with me. But after this, you probably get more detailed information than you will ever get out of a study called Plant Sciences, which I happen to have followed during my days as a student. So I have my laptop in front of me, so that gives me the opportunity to every now and then look at some better pictures. And besides that, I do have a little bit of like paper in front of me so that I can just draw things out. So you will just see me pause the video and I'll put all of the fragments together and then make one big video out of it. So I think if we are thinking about the first step that I want to go over, it's probably where it all starts. So if you look at this is a membrane with what we are now going to look at is photosystem 2, because photosystem 2 is called photosystem 2, I believe, because photosystem 1 was first found. I see it also needs light. It's interesting. I think that photosystem 2 is the one with the antenna complex. And I'm not too sure about that. So if you want to know for sure about that, then you have to verify that yourself. But I'm going to look at photosystem 2 because I believe that this is where the antenna network is located and this is where the light is going to be absorbed. So if you look at photosystem 2, then actually a more detailed picture of it is this one here. So yeah, that makes sense. So you have a reaction center. That's where the electron that's captured is eventually passed to the excited electron, and that's going to actually do some things and do all these things, which is not truly interested into if you're interested in the light thing. So if I say that, so what you need to know, first of all, is sort of that you have a lot of these different pigments. So you have chlorophyll A, chlorophyll B, you have carotenoids, and I believe there are plenty of pigments that can lay around in photosystem 2. And what you need to know is that light are actually just photons with a certain wavelength. And in that wavelength is energy. And that energy can be used of those photons, so those rays. So those rays with energy, they hit one of the free living electrons in one of these pigment molecules. And that free living around electron is excited to a higher state, which gives the free electron more energy. And when that thing happens, that excited electron is transported through, and I can show that like this. So let's say there comes a beam of light, which is my cursor here, and it happens to, let's do this, fall on this one. It excites an electron, and that electron is then free, and then it's transported all the way to the reaction center. And then here is where some magic happens and stuff happens. But I see that the timer is saying that I almost need to quit and start a new one, so I will do that before I actually go on to what happens. So, nice. We're back. What I wanted to say is, if this didn't make sense at all, then you probably need to look at YouTube or Google what exciting this stuff means. Just make sure for now that every one of these pigments has a different wavelength that they can absorb. So to put it into simple words, every one of these uses a different kind of light. Well, I don't like the term light. That's because I like to be very practical and I prefer to use the word every one of these absorbs photons with a different spectrum of wavelengths. And now things get interested because I think, if I remember correctly, chlorophyll A absorbs red light, chlorophyll B absorbs blue light, carotenoids absorb more yellow light, and that's it. So that's good to know because that allows this entire complex to actually absorb all different kind of photons that come from the sun. But now let's say, okay, well, I'm actually going to do this because this is where things get very difficult. I actually want to see if I can find a picture of something that illustrates this a little bit better so that we digest this material just a little bit easier than it's now, because now it's a lot of words and it's difficult to digest maybe. So just give me a second. So that's it. I'm back. And what I'm looking at here is just very simple. This is blah, 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 like this. So what I have here is that you have a higher energy because the wavelength is shorter. So blue light, higher energy, red light, lower energy. And I think this is another one that I wanted to show because... So what I just showed on these pigments is that if you only have chlorophyll A, for example, then you have the peak around red light. If you have chlorophyll B, you have the peak around blue light, and you have carotenoids, and it's also a little bit of blue light, but a little bit more shifted, and green light is underrepresented. Yeah, I'm not going to jump into conclusions about that. But what you can see is that so every one of these pigments has a different part of the spectrum that they can absorb. So yeah, interesting stuff. If you don't follow along, then you probably have to digest some information. Oh wait, this is not what I wanted to do. I wanted to go for this one. So photon energy, like I just said, it's not really, that's just a formula. Just know that the energy of red light is smaller than the energy of blue light. And I might be thinking, well, blue light has more energy, so that's better, right? And that's not true, because the energy that the photon contains is not really relevant at all. Maybe I shouldn't emphasize because I'm checked if it's not relevant at all. But what I can say is that the thing that's most important for photosystem 2 is photons. So it doesn't matter if you have, for example, let's make it a little bit more practical. It doesn't matter whether or not you have 1 million photons which weigh 1 kilo or 1 million photons which weigh 10 kilo. As long as you have 1 million rays coming, then this happens. It just is a matter of 1 million rays get intercepted and get carried here. So this system where the electrons splits out happens 1 million times. The energy of the electron doesn't matter as long as it just happens 1 million times in this time. So that's what I wanted to emphasize here. So now you might be wondering, does it really... Okay, let's actually pause. Let's pause because now we're going very quickly. So the thing that I wanted to say is all what matters is that the reaction center gets ignited as many times as possible. And then you might think to yourself, wait, but what if we only excite chlorophyll A with red light as many times as we can? And we just ignore chlorophyll B and carotenoids. What if we do that? Because it costs less energy, I believe, to generate red light. So you get more photons per joule of energy. And for that reason, you could say, hey, I save energy by just putting in red light into this system because it's just all about the photons. And then I say, no, we are talking. Because that's the whole philosophy behind it. And then things are super interesting because it is true. But then we are going into the nitty-gritty little nitty-gritty details. That's it. Yeah, because so first you just want to excite the reaction center as many times as possible, and we don't really care how you do that. So how do you do that is then the question. I think I just need to write that down on the paper again, just to make some sense out of it. So here we are, just back, and I wrote down what we are going to for. So just to make clear, the objective is to excite the reaction center as many times as possible without wasting photons with the least amount of energy. So we don't want to waste any red photons, and at the same time we want to optimize the amount of times that we activate the reaction center. And because red photons are cost the least amount of energy, we use red photons for this. And then the first thing is like how many excitations are needed for the plant. And that's why we have a new concept, and that's why we are going back to this thing, because actually I need this one. So what happens is this system happens at the edge of these green boxes, which means that the environment inside the green boxes is different than the environment outside of it. And that's important to know because, as you can see here, this photosystem 2 splits water into H+. The H+ in this telecalloid lumen, so that's inside the discs, becomes very acidic, and this acidification is used to convert ADP into ATP, which is energy, and also this stuff. So it does a lot of things. And why that's so crucial to know is because what we want to sort of reach is the point where all of the ADP is converted into ATP, so that the ATP can be used to convert CO2 into sugars. So that's the entire cycle that we're aiming for. Like if all the ADP is converted to ATP, so that means that the sugar production is too low, then it doesn't really make any sense anymore to absorb more photons into photosystem 2. Because we are building more H+, but we don't have any molecules to convert. So that's why this DLI concept exists. And at the same time, so you have a certain maximum amount of photons that a plant needs every day. But if we have too little photons to actually convert enough ADP, so that means that the plant is actually starving. So if it receives too little light, then it can produce enough ATP, which means that it can produce enough sugars to actually, first of all, maintain its own cells so that they keep on living. And the second of all, then it certainly doesn't have any ATP left to actually invest into growth. So this is why the DLI is very important, as I wrote down here. And the DLI is, I believe, is just the number of hours multiplied with the photon flux density, which is that the plant requires approximately 800 micromoles per square meter per second, something like that. And then you multiply it with the amount of hours that the plant needs light. So species, plants like lettuce, which are a little bit more sensitive to oh dang it, that's a dog, are a little bit more sensitive. Nala, kom eens hier. It's good that people know on this channel already that I'm Dutch, so it's not a surprise that I actually switched to another language for this. But anyway, so if a species is incapable of using all of this light, actually I'm confusing two things here a little bit, but there is some truth in this. I'm actually gonna let the dog out, even though I know that the dog will come in very quickly. Let me get a brief pause. So that I changed position. What I wanted to say is I kind of lost track of where I'm at, and I could simply look back, but I'm not doing that because I'm already recording and I'm kind of lazy. So let's stop that one here. Cool. What I wanted to say, I think where I left off, is here. So I think I just talked about like objective 2, which is that we want to ensure that the plant receives enough photons to convert all of the ADP into ATP for sugar production on a day-to-day basis. So we limit ourselves to that we may only use red light because it's the most energy efficient for photons, that we don't waste any photons, and that we convert every EDP on a day-to-day basis. And the challenge, first of all, is that most photosystems for red light are near the surface. So I found this video, and I will show the YouTuber right now, which does it. So that's Albo Pepper. Now I need to make it full size again. There we go. So this one illustrates this very nicely. Red light is only absorbed in the top part and not so much deeper in the leaves. Why is this problematic? Well, because we are going to apply only red photons, which means that we don't reach all of the photosystems that we can potentially reach. And I want to pause for a little second here, because what it means theoretically is if we use all of the photosystems, then we convert much more EDP into ATP much more quickly. And our goal is to convert all of the EDP that the plant has on a day-to-day basis so that we have obtained maximum growth. Well, great. I mean, it just takes longer to get the same amount of EDP conversion to EDP if we only use red light. And this is completely true. So far, there's not really any problem on the horizon. We just need to be more patient and more efficient. So that's good. So no problem yet, right? Well, here's the thing. We have a concept called photo inhibition. And I wrote it down. If you don't know the concepts, look it up. Those concepts are nice. And the problem is that you have a point where the reaction centers are saturated, which is dependent on the flux. And the flux is nothing more than the amount of photons which lands on a square meter per second. And if more photons, if the amount of photons that lands in a square meter per second exceeds the capacity of the reaction center, then we get a thing called photo inhibition, which means that the energy is lost through heat or other processes and might even cause damage to the plant. So we know our limitation right here. So we are already limited in the amount of cells that we can actually use for photosynthesis, and we are also limited by this reactive center capacity. So now we can go back, not to my face actually. Now we can go back to this picture, and it means that we also limit ourselves only to the bottom one. So these chlorophyll A pigments are already limited. So we use limited cells for photosynthesis, and then we also use the limited capacity of a photosynthetic pigment, of our photosystem too. And I'm quickly going to pause and do this again because otherwise it will fall out. So what I wanted to say is that this step where an electron is transported to the reaction center and then this jump of the electron happens, what that in theory is that this whole cycle is being started. So if the amount of electrons that are being transported to the reaction center exceeds the amount of times that this whole reaction can happen, then there needs to happen something with the electron, because otherwise it damages it causes damage to the plant. So then it becomes a matter of, okay, so how do we know the equilibrium? So how many photons do we need to send out per square meter per second to a photosystem 2? And actually I need to write this down because it gets way too complex right now, because now we are getting to very sophisticated and complicated systems. So let me write this down quickly. So I think that despite I don't earn a degree on arts, I think this does a very good job at explaining the issue exactly. Why is such a sophisticated thing? So we have an LED, and the LED sends rays of photons. Some photons go all the way to the sides, and some photons actually, let's do it like this, because this explains. I shouldn't just talk when I'm actually with something more. So the thing is, the plant just underneath the LED light receives, you guessed it, more photons than the plant that's right beside this light. And that poses an issue, because this one can convert less EDP into ETP than this one. Which means that one of these plants, either one of these plants is starving, or one of these plants' reaction center capacity is actually exceeded. Okay, so how do you solve that? You can just put another LED above here. So, and then you determine that neither of these plants' reaction center capacity is exceeded. Okay, that's great. That's one solution, of course. But yeah, one cell consists in both, like horizontal and vertical, out of a lot of cells. And every cell has multiple chloroplasts. And every chloroplast has these thylakoid sets of thylakoids. And on the membrane are the photo-2 systems. So you can guess that where the photons land, that every one of these reaction centers receives just a little bit more or a little bit less photons based on which layer of the cells it are, where the LEDs and the photons are going to and is located, and where the plant is located. So there is a lot of uncertainty in this case. And another big issue is that, let's look at this one. Let's say that theoretically speaking, we can make sure that every one of these chlorophyll A's receives just enough photons that the reactive center is never exceeded. Then the amount of pigments of chlorophyll A in every one of these photosystem 2 can vary. And that's very problematic, because what if the neighboring photosystem, has double the amount of chlorophyll A? Then we can just double the amount of photons that we input, because the one with less chlorophyll A is going to receive photo inhibition. So we need to minimize the amount of photons that we send towards these systems, so that it never, ever, one of these photosystems ever exceeds the capacity of the reaction center. Well, that's certainly a challenge. I mean, it may never exceed one of these centers. So it pretty much means that we need to have very low light conditions in order for all the photons to be absorbed. Which means that if we have very low light conditions, we need to constantly and provide a lot of hours with light in order to convert all the EDP into ETP. And everyone, that's actually where we can almost round things off. And I will quickly reset this one and start a new clip, but then I will discuss why. So before I round things off, let's actually think about one more thing, because I talked about this starving. So you want your plants to grow, and because you want your plants to grow, there of course becomes more EDP that needs to be converted into ETP the bigger your plant grows. Well, I mean, look at how many cells, so I'm very sorry for that. I mean, look at how many cells are black when you provide only red light. That means that all of those cells are not producing ATP, but need ETP to be maintained. So if you have multiple layers of leaves, then only the top of the canopy can actually use red light and needs to only the top leaves are going to produce energy for the plant. So the more leaves it gets, the quicker it will starve out and the more its growth will be ramped. Which means that you will need to have a lot of reflectivity and a lot of LED lights from the sides as well. And it pretty much means that you need to make an impossible setup with red lights to provide the plant with enough energy to provide the plant with enough energy to maintain all of the conversion of EDP to ETP without wasting any photons and cause photo inhibition. Yeah. And then, of course, you have the malfunctioning of your plant because plants are evolved to use the full spectrum of light. It would be kind of dumb if a plant got offered every sort of radiation from the sun and then decides like I only decide to pick the red light of what you offer me and no thanks to all of that other free energy that you provide me with. I will just leave that to some kind of brick wall. Let it absorb it, I'm just fine taking red. No, of course not. Then those plants wouldn't really evolve to what they are today, to big trees and whatever. They need to be efficient with all of the energy that they can capture. So of course they evolved systems to use green light, use blue light, use UV radiation, use infrared radiation, use yellow light. They all evolve because they want to use the energy that the sun provides to them as much as possible. So, yeah, if you then ever wonder, like, hey, cool, I have this red light and this blue light, and it's probably more efficient. I mean, theoretically speaking, I could still make an argument because I didn't do the calculations. Let's be clear of one thing. I did not do the calculations to determine how much red light you need. I'm going to try and experiment with that in the future because I actually want to know the answer, and I think I can already guess the answer that if you want to be energy efficient and save as much energy as possible, then you will eventually stumble upon the fact that your plants are limited in growth and you don't want it either. So I think it's just gonna be a failed experiment, but anyway, I'm just gonna try it for fun. And of course you can use red light for optimization, but I mean, yeah, the ideal situation that people are striving for, it's I think a little bit like not realistic. But like I said, there's only one counter argument to this, is that if you don't really care about how your plants look like and you just want to create as much biomass as possible, then there might be an argument to that this is feasible. The only downside of that is that you deliver a lot less quality plants because something like UV radiation is essential to create flavonoids, and you need red light, or what is it? You need, for example, I believe yellow light to make carotenoids, or at least just take this from me. I'm very certain on the flavonoids. You need UV radiation to make flavonoids because I believe flavonoids and other antioxidants are produced by the plant to defend itself against UV radiation, and it's exactly those compounds, those flavonoids, antioxidants, that are very healthy to us humans. So if you want to consume a plant that's basically only been fed with red radiation to produce sugars, then you might as well tell yourself like, hey, if I don't really care about if I eat healthy food, then I might just as well consume sugar directly, like buy a pack of sugar in the supermarket and consume as much as I need just to get on with my day and meet my requirements for energy consumption. I can tell you, probably nobody thinks that's a good idea, and I can tell you I would not recommend it at all. So that's basically the conclusion. Like, there are a lot of people who do like extensive research on like which white lights are the best. Just know for a fact that now if people are telling you that white lights are good, that there is like a very clear reasoning behind why white light is very good. So I hope you like this. Of course, if you don't understand concepts, or if you if you want to back check me, I would totally invite you to just look up the concepts that I just spoke about, because as far as I know, you should come to the same conclusion if you look into the things that I just explained. Anyhow, that's it for this video. Hope that it helped some people with the question which light they need to use for their plans. I'm just going to keep this in the back of my mind and once see what I can get out of the knowledge that I just shared with people. Have a good time. Look around for other YouTubers to look for some reviews. That Elbow Pepper is very good. Would recommend him. And for the rest, hope you enjoyed this video. And I hope that you enjoyed the rest of your day. See ya. Cheers. Goodbye. You thought that I ended the video, and I thought so too, but I just wanted to show one quick thing. Because the concept that I just explained, with like if you only use red light, of course, if you can't meet the demand of your plant's conversion from EDP to EDP, you can actually apply the same concept to use another band. So let's say we only focused on chlorophyll A pigments in this case, then of course what you can say is, hey, what's the next most efficient pigment that we can actually use to excite these pigments in photosystem 2. So we increase the amount of times that the reactive center is activated, and by activating the reactive center more times we get more conversion, so maybe then we don't have a plant that starves out. And then of course you get something like this. So you would buy a couple of LEDs which are very efficient in producing the red light, and then you buy a couple of LEDs which are very efficient in showing in the blue light. And then it's of course about the efficiency of those LEDs. So okay, you know that red light is the cheapest in terms of output in photons, and then you say, okay, I just can't make it with the red light itself, so I add an extra color, and then I choose for blue. I think I can tell you about all of my research is that of course I would prefer yellow light, because yellow light contains more energy per or more photons per energy. However, that's not how LEDs work. LEDs, as far as I know, they have like certain molecules. One of them is, for example, metal, which has a surplus of electrons, and the other side of the LED contains metals with a deficiency in electrons. And then depending on the deficiency and the surplus of the metals, there comes a little band in the middle of the two metals, and the size of that band determines which when there is like electrons going through, which is a current, then the excitement of that band determines which light comes out of that. And as far as I know, people only use metals which have either emit blue light or either emit red light. I think they even emit actually a spectrum which is related to temperature color CCT. Or actually no, might not be. I'm a little bit, as far as I know, this is the basic. And what happens then to get more full spectrum is that they add phosphorus or something like that, so that the phosphorus takes up some of the photons and then re-excites it so that you get a full spectrum. If that all went too fast, it can happen. It's quite complex, but the main takeaway that you need to know is that most LEDs either start as a blue or red LED, and there is no LED that starts as a yellow LED. And then if you convert the blue LED, blue photons from a blue LED to a full spectrum, then upon the interaction of the photon with the phosphorus, it excites, it sends out different wavelengths, but at the same time it's at the cost of some heat getting out of the system. And because heat is generated, of course you lose energy and it becomes less efficient. So I wanted to quickly say that, because let's say the red one isn't enough, but then you add blue light to it and then you meet the demands of your plant, then great, you know, then we are still at the point we have still done the most efficient. We've still developed a system that's the most efficient to our ability, energy wise. But of course, as I showed in that one video, is that blue and red light is near the surface, and that the cells that are a little bit deeper in the canopy or deeper within the cells, those are not participating. So eventually, if the plant becomes too big, then the top cells need to generate a lot more ETP to actually make up for all of the loss, for all of the maintenance cost of the other cells that are not participating in it. So the conclusion remains kind of the same that I said. Just stick to white light. It's healthier for your plants. It's healthier for yourself as well because of the flavonoids. And yeah, there are so just many, and plants have evolved to use a full spectrum. So there are reasons that it's actually very efficient. But yeah, this was just see it as an appendix to what I just said, so that you maybe can apply this concept a little bit further. I'm not gonna say the same thing like I just did. I just gonna say, have a good day. I hope you have a good day. Cheers and goodbye.